aware that you guys hadn't seen the quadratic equation before. So anyway, we need to just go over chapter 14 a little bit more and talk about, again, drive home like what this concept of equilibrium is so that you can figure out how to solve questions as they come, okay? So again, I just want to drive home that if we have anything, a plus b will reach equilibrium with AB, let's say, or here, let's spice it up a little, 2A there. Okay, basically what equilibrium means is, if I say this reaction is currently at equilibrium, what I'm saying is that I can't see any changes occurring. It looks to me like I have a certain amount of the species B present, a certain amount of the species A present, and a certain amount of the product present, okay? It doesn't mean that the amount of reactant is equal to the amount of product, but it does mean that the proportions between them won't be changing. So that's why we have something called Kc, an equilibrium constant, okay? It basically, it is just a proportionality constant, really. It gives us the concentration, assuming this is all aqueous, it gives us the concentration of our product raised to the stoichiometric coefficient, which in this case is just a 1, divided by the concentration of our reactants, raised to their stoichiometric coefficient. So here there's a 2, so I'm going to raise the concentration at A on the bottom to the power of 2. And it really is that simple. So what the idea is, if the temperature were to remain constant, I can add, additional A, I can remove product, but this Kc will not change, meaning that the system will go ahead and readjust itself regardless of what I change in the concentration, let's say. The system will readjust itself in order for Kc to stay constant, okay? That's, again, assuming that we're at equilibrium. There's a couple more things to say about this. Notice I didn't put here what the states were. Let's say that A, or let's just say that B was a liquid. I would not include it in my formula, okay, for Kc, for the equilibrium constant. If it were also a solid, I wouldn't include it. The only things I'm including here would be, let's say, gases we can do Kc for, and aqueous solutions we can do Kc for. And then we also talked about how if let's say that this were gas, and gas, I can measure Kc, which will be a constant, but I can also measure something called Kp, which is basically, it's the exact same thing. It's the product over the reactant raised to their stoichiometric coefficients, but I can just measure the partial pressure instead. So I'm going to say partial pressure of A squared, partial pressure of B on the bottom, and partial pressure of product on top. So Kc and Kp are really, they're the same thing. They're just these constants that are specific to that reaction at that temperature, okay? And that's really the most important thing for us to understand. If you understand what this is, then you can understand how to work out problems that involve Kc, Kp, or another one, Qc, which we also talked about, okay? Now, I told you that this equation is currently at equilibrium, but how did it get there? I mean, let's say a reaction begins, and we begin with 2 moles of A and B. Let's pretend they're both in aqueous solution. Okay, what's going to wind up happening at first is A is going to react with B, and I'm going to start creating product, right? So A reacts with B, A reacts with B, A reacts with B, and I start making product. Can I see something in the laboratory changing? Yes, I can, okay? But what's going to wind up happening is it's going to make a little bit more product than is wanted, okay? And so this product is going to start re-reacting. That's why I drew the opposite arrow, to form reactants again, okay? So I have the concentration of reactants decreasing to form the concentration of product. Whoa, and now suddenly also at the same time the concentration of product is decreasing to form the concentration of reactants. So at some point in time, the speed or the rate at which the A and the B is combining will be equal to the rate at which the product is dissociating, okay? And at that point, is there a change occurring? Yeah. the reaction is still going, it's going both directions, but I can't see any changes, right, because I'm at equilibrium, okay? Now, how, if you're actually in the laboratory, how can you tell maybe what's going on a molecular level? Well, that's where QC comes in hand, okay? Like, let's say it's the initial, it's the beginning of my experiment, okay? And, you know, it's only 5 seconds in the experiment, and I have 2 moles of, you know, let's say, I don't know, 0.2 molarity of A, 0.2 molarity of B, and 0.1 molarity of product, okay? Like, how do I know how far away I am from equilibrium? Well, that's where QC can come in hand. I do the exact same calculation at case that I do for KC, okay? By the way, this is called the reaction quotient. So from this point on, I'm not going to say QC and KC. I'm just going to say reaction quotient and equilibrium constant, okay? So for the reaction quotient, I'm just going to do the exact same calculations as I would do for the equilibrium constant, but I have to keep in the back of my mind that this may not be at equilibrium, okay? And this is really important because they're going to throw out problems at you guys, and you're going to need to know, you know, like they might give you initial concentrations. I noticed people were doing that yesterday in class. They might give you initial concentrations, and you go and think that that initial concentration can calculate the equilibrium constant. No, it can't. If it's the initial concentrations that they're giving you, then that only gives you the reaction quotient, okay? Now, after you calculate the reaction quotient, you might get QC equal to KC, maybe. The reaction quotient may be equal to the equilibrium constant, again, assuming it's not the initial now. That would mean simply that, okay, this reaction is at equilibrium. But QC might be greater than KC. Your reaction quotient might be greater than your equilibrium constant, in which case that means that I look mathematically now, I have too much product. The top, in this equation, the top is too heavy, okay? So if the top is too heavy, then that would mean that in order for this reaction to reach equilibrium, it's going to shift. Let me do this from your right to your left. I'm doing this upside down. Then the reaction is going to shift from product to reactant because it has too many products. If QC, the reaction quotient, is less than KC, then that simply means that it's too heavy on the bottom. There is a higher concentration of reactants than need be at equilibrium. Therefore, the reaction will be shifting towards the product this way. So that's one way you can play around with QC and KC, but more importantly, what I want to worry about is how we can solve the problems involving an ice table. And we did one of them yesterday, again, because I think the most important thing for you is to be able to identify when you actually have to do a problem that involves an ice table. So I'm looking through the book as I talk actually right now. We did in class some simple problems where they would give you a certain reaction, and then they would ask you for KC, like they would ask you for the equilibrium. That's a question mark, by the way. They would ask you for the equilibrium constant. So all you'd have to do is plug in concentrations for everything. Okay. But yesterday you had a problem that was a little bit different, and we only did like 2 examples in class, so I wanted to make a video on this. We have a reaction here. They're saying a mixture of hydrogen gas and iodine gas. So I'm going to say, this is actually I think the same one we did. This is the same reaction we did in class yesterday, but it's just different numbers, I think. So we have a mixture of hydrogen gas and iodine gas, okay, and it's placed in a 1 liter stainless steel flask at a certain temperature Celsius. Now, hydrogen iodine gas, as we know, is going to make equilibrium. It's going to become hydrogen iodide. That's number 2. It doesn't look like a 2. That's a 2. Gas. Okay. So here's our reaction, and they're telling us that we have a half of a mole of hydrogen gas and a half of a mole of iodine gas. Okay. And it's in a 1 liter flask, so it's basically 0.5 molarity, 0.5 molarity. And they didn't give me, they said this was placed with this, right? So I'm going to assume that these are initial concentrations before I write it here. I'm going to write I for initial, and then I'm not even going to do that yet. Okay, so I'm going to assume that I have initial concentrations of 0.5 molarity, 0.5 molarity, and they didn't give me they didn't give me an amount to start with for product. We talked about that as well in class. If they don't give you an amount to start with for your product, what does that mean? It probably means I don't have any to begin with, which is logical, right? Because the reaction just started. This is my initial concentration, so initially it makes sense that I wouldn't have any product yet. This is not always the case. Sometimes they'll give you a reaction, let's say 5 seconds in, where you have a little bit of reactant and you have a little bit of product, okay? Or they'll give you a reaction where there was already some product available. So this is not always zero. Just watch out for that. However, if they do not give you an initial molarity for your product, it's safe to assume that it's zero, okay? Anyway, now they're also giving us Kc. And they're saying that for this reaction at this temperature, Kc is 54.3, okay? And remember, Kc does not have units. I forgot to mention that. The equilibrium constant does not have units. We don't even bother with the units. We don't care. And that's why you'll also notice here, it's one of those few times you'll see me not writing out the units because I don't care. Kc is a unitless quantity. Okay, so now their question is, calculate the concentrations of hydrogen, of iodine, and of my hydrogen iodide at equilibrium. Okay, so if I wanted to make a given table, I'm given Kc, and I want the concentration of hydrogen at equilibrium. Again, there's 2 right there. Of hydrogen, of iodine, I2, and of hydrogen iodide. I want these concentrations at equilibrium. I want all of them at, that's a backwards, EQM, okay? And we talked about in class, if I have Kc, yes, I can get the concentrations at equilibrium, provided I know what I started with, okay? So they gave me initial concentrations, and then they gave me Kc, and now they want me to find my concentrations of everything at equilibrium, okay? This is...